March 15, 1945, Tinian Island, Mariana Islands. Captain Robert Morgan stood before the massive aircraft that would carry him and 10 other men into the stratosphere above Japan. The Boeing B-29 Superfortress, designated Dauntless, Dottie, stretched 30 meters from nose to tail, its polished aluminum skin gleaming in the tropical sun. 4 Wright R3350 duplex cyclone engines, each producing 2,200 horsepower, hung beneath wings that spanned 43 meters. This was not just another bomber. This was the most technologically complex aircraft ever mass, representing an engineering gamble that had cost more money than the Manhattan Project itself. Morgan climbed through the forward hatch and immediately felt the difference. Unlike every other bomber he had flown, the B-29's interior was shirt-sleeve, comfortable even on the ground. No bulky heated suits required, no oxygen masks dangling from overhead connections. The pressurized cabin system maintained sea level, atmospheric conditions even when the aircraft flew at 30,000 feet, where outside air temperature dropped to -40 degrees and oxygen was too thin to sustain consciousness. This single feature, this one revolutionary system, had consumed 3 years of development, cost hundreds of millions of dollars, added thousands of pounds to the aircraft's weight, and saved the lives of thousands of American airmen. But the price for this protection, both in engineering challenges and operational compromises, had nearly destroyed the entire program before a single combat mission was flown. The journey to this moment had begun on January 29, 1940, when the United States Army Air Corps issued a requirement that seemed impossible with existing technology. The specification demanded a bomber capable of carrying 2,000 pounds of bombs for 5,333 miles, at speeds exceeding 400 miles per hour, capable of operating at altitudes above 30,000 feet, incorporating armor protection for crew, self-sealing fuel tanks, and heavy defensive armament. No aircraft in the world came close to meeting these requirements. The B-17 Flying Fortress, America's frontline heavy bomber in 1940, had a range of approximately 2,000 miles with bomb load, cruised at 182 miles per hour, and operated effectively at altitudes around 25,000 feet. The British Avro Lancaster, not yet in service but under development, would achieve similar performance. German bombers operated at even low altitudes, with shorter ranges. The Army's requirements demanded an aircraft with more than double the range, significantly higher speed, and the ability to operate in the stratosphere, where no bomber had ever flown operationally. The strategic context for these requirements reflected American military planning in early 1940. War in Europe had begun in September 1939. German forces had demonstrated the effectiveness of air power in the Polish campaign. British and French forces faced a technologically sophisticated enemy with proven military capabilities. American planners recognized that the United States might eventually be drawn into global conflict. More critically, planners understood that America's potential enemies in both Europe and the Pacific were separated from American territory by vast ocean distances. Any future conflict would require striking enemy homelands from bases thousands of miles distant. Existing bomber technology could not achieve this strategic reach. American bombers could strike targets within a few hundred miles of their bases. They could not cross oceans, penetrate enemy airspace, strike industrial targets, and return home. The requirement for a 5,333-mile range reflected calculated distances to potential targets in both Europe and Asia from bases that American forces might realistically establish. The altitude requirement was particularly challenging and reflected lessons from early air combat in Europe. At 30,000 feet, atmospheric pressure drops to approximately 1/3 of sea level pressure. Outside air temperature falls to -40 degrees Celsius or colder. The human body cannot function in these conditions without supplemental oxygen and protection from cold. Every bomber then in service handled this problem the same way, with oxygen masks for crew members, electrically heated flight suits, and acceptance that crew would operate in extreme discomfort throughout missions lasting 8 to 10 hours. Pilots wore bulky leather jackets, lined with electrical heating elements. Gunners stood at their positions in temperatures cold enough to cause frostbite within minutes of exposed skin contact. Oxygen systems required constant monitoring to prevent hypoxia. The physical demands of operating in these conditions reduced crew effectiveness and increased fatigue dramatically. Missions at 25,000 feet already pushed crews to their physiological limits. Operating at 35,000 feet with conventional systems would be impossible for missions lasting 10 to 15 hours. Boeing's design team, led by Chief Engineer Edward Wells, proposed a solution that had never been implemented in any production military aircraft: a fully pressurized cabin that would maintain comfortable atmospheric pressure and temperature regardless of outside conditions. Wells had joined Boeing in 1931 after graduating from Stanford University with a degree in mechanical engineering. He had worked on multiple Boeing projects, including the Model 247 commercial transport and early B-17 variants. Wells understood both the theoretical possibilities of pressurization and the practical challenges of implementing such systems in operational aircraft. The concept was not entirely new. Experimental aircraft had tested pressurization systems in the 1930s. The Lockheed XC-35, which flew in 1937, demonstrated that pressurized cabins were technically feasible. Wiley Post had flown pressure-suited flights at extreme altitudes in 1934 and 1935, proving that humans could function at stratospheric heights with proper equipment. But no aircraft had ever attempted to incorporate pressurization into a production bomber, while also meeting requirements for range, speed, altitude, and defensive armament. The engineering challenges were formidable and interconnected in ways that would create cascading problems throughout the development process. A pressurized cabin requires a pressure vessel, an airtight structure capable of maintaining internal pressure significantly higher than external pressure. At 30,000 feet, the pressure differential between inside and outside the aircraft would exceed 8 pounds per square inch. This differential creates enormous stress on the fuselage structure. Every square foot of cabin surface experiences 1,152 pounds of force trying to rupture the pressure vessel. Over the B-29's cabin area of approximately 600 square feet, the total force exceeded 690,000 pounds, nearly 345 tons of force constantly pushing outward on the fuselage skin. The structure had to contain this pressure through thousands of flight hours, through violent combat maneuvers, through battle damage that might puncture the pressure vessel, through temperature cycles that ranged from tropical heat on the ground to Arctic cold at altitude. Any failure of the pressure vessel would be catastrophic, resulting in explosive decompression that could kill crew members instantly or damage the aircraft so severely that it could not return home. Boeing engineers designed the B-29 with 3 separate pressurized compartments, connected by a pressurized tunnel that ran above the bomb bay. The forward compartment housed the pilot, co-pilot, flight engineer, bombardier, navigator, and radio operator. This compartment occupied approximately 15 feet of the fuselage length and provided roughly 400 cubic feet of pressurized space. The rear compartment, located aft of the bomb bay and wing section, housed the tail gunner in isolation from the rest of the crew. This compartment was significantly smaller, providing just enough space for one crew member to operate the tail gun position. The tunnel connecting these compartments was barely 30 centimeters in diameter, just large enough for crew members to crawl through while wearing flight gear. This configuration reflected the reality that the bomb bay could not be pressurized since bomb bay doors must open in flight to release weapons. The tunnel allowed crew movement between compartments while maintaining pressurization throughout the mission. But the tunnel itself presented extraordinary engineering challenges. The tunnel design required solving multiple conflicting requirements simultaneously. It had to be pressure tight, maintaining a seal despite the differential pressure between inside and outside the aircraft. It had to be flexible enough to accommodate airframe flexing during flight. Since the fuselage structure bent and twisted under aerodynamic loads in ways that would rupture a rigid tunnel, it had to be strong enough to support crew members crawling through it, withstanding the weight and dynamic forces of men moving through the narrow passage during turbulent flight. It had to be small enough not to obstruct the bomb bay or interfere with bomb release mechanisms. It had to be long enough to span the distance from forward compartment to rear compartment, approximately 30 feet through the center of the aircraft. It had to be accessible for maintenance and inspection, since any leak in the tunnel would depressurize both compartments. The final design used a series of cylindrical segments constructed from aluminum sheet, joined with flexible bellows sections that could accommodate airframe movement while maintaining pressure integrity. Each segment was approximately 3 feet long. The bellow sections between segments allowed flexing of several inches in any direction. The interior was lined with padding to prevent injury during the awkward crawling required to traverse the tunnel. The pressure vessel's structure required radical changes to conventional aircraft construction methods that had evolved over 2 decades of aviation development. Standard aircraft fuselage used longitudinal stringers and circular frames covered with aluminum skin. The skin carried minimal structural loads, serving primarily as an aerodynamic surface. The stringers and frames provided strength and stiffness, carrying flight loads and maintaining fuselage shape. This construction method, called semi-monocoque, had proven effective for unpressurized aircraft, but it could not contain pressurization loads without fundamental redesign. The outward pressure on every square inch of skin would peel the covering away from stringers, unless the skin itself became a load-bearing structural element. Boeing engineers developed an enhanced semi-monocoque structure, where the aluminum skin itself carried major structural loads, in addition to the stringers and frames. The fuselage skin thickness increased to approximately 2.5 millimeters in pressurized sections, nearly double the thickness of conventional bomber fuselage skin. This thicker skin had sufficient strength to resist the outward pressure, while also providing the aerodynamic surface. Longitudinal stringers were redesigned to share loads with the skin rather than carrying loads independently. The stringers and skin worked together as a structural unit, distributing pressure loads across both elements. Circular frames were strengthened and spaced closer together to resist the outward pressure that tried to expand the fuselage like a balloon. Every rivet, every joint, every penetration through the pressure vessel had to be sealed perfectly. A single leak could depressurize the entire cabin, reducing the system to uselessness. The sealing requirements imposed manufacturing challenges that exceeded anything Boeing had previously attempted. Conventional aircraft manufacturing tolerated small gaps and imperfect fits between components. Aerodynamic performance suffered slightly from poor fits, but structural integrity remained unaffected. A pressurized aircraft could not tolerate any gaps or leaks. Every joint had to seal perfectly. Every rivet hole had to be completely filled. Every access panel had to close with airtight seals. Every penetration for control, cables, electrical wiring, or hydraulic lines had to incorporate pressure seals that maintained integrity through thousands of pressure cycles. Boeing developed new manufacturing processes specifically for B-29 production. Workers applied sealant compounds to every joint before riveting. Inspection procedures included pressure testing every fuselage section before assembly to identify leaks. Special tools and techniques ensured that rivets filled holes completely without gaps. Access panels incorporated rubber seals compressed by closure mechanisms to create airtight barriers. The attention to detail required for pressure-tight construction dramatically increased manufacturing time compared to conventional aircraft. Each B-29 fuselage required approximately 8,000 additional man-hours of labor compared to a B-17 fuselage of similar size. Much of this additional time devoted to sealing procedures. The weight penalty for pressurization was enormous and affected every aspect of the aircraft's design. The strengthened structure, thicker skin, pressure-tight joints, redundant sealing systems, and the tunnel connecting compartments added approximately 3,000 pounds to the B-29's empty weight. This represented roughly 8% of the aircraft's total empty weight of 36,500 kilograms. Every kilogram added to structural weight reduced either range or payload capacity through the inexorable mathematics of aircraft performance. An aircraft has a maximum takeoff weight determined by wing area, engine power, and structural limits. This maximum weight is fixed by design. The total weight is divided between empty weight, which includes structure, engines, systems, and equipment, fuel weight, which determines range, payload weight, which includes bombs, ammunition, and crew, and operating reserves, which includes oil and emergency equipment. If empty weight increases, either fuel weight or payload weight must decrease to maintain the same maximum takeoff weight. Alternatively, maximum takeoff weight must increase, which requires larger wings or more powerful engines, both of which add more weight and create a spiral of increasing weight that rapidly becomes unmanageable. The Army's requirements demanded specific performance in range, altitude, speed, and bomb load. Adding 3,000 pounds for pressurization meant that other systems had to be lighter or more efficient to compensate, or engine power had to increase to carry the additional weight without sacrificing performance. Bowing engineers conducted detailed weight analyses of every component and system. They identified opportunities to save weight in non-critical areas to offset the weight penalties for pressurization. They used aluminum alloys with higher strength-to-weight ratios where possible. They designed structural components to minimum gauges that still provided adequate safety margins. They eliminated unnecessary equipment and systems that did not directly contribute to mission requirements. But even with aggressive weight reduction efforts, the pressurization system still imposed a net penalty that required more powerful engines to maintain performance. Boeing selected the Wright R3350 duplex Cyclone engine for the B-29, an 18-cylinder radial producing 2,200 horsepower. This engine represented the cutting edge of American aviation technology in 1940 and incorporated features that no production aircraft engine had previously used in combination. The R3350 was a massive piece of machinery. It weighed approximately 2,700 pounds dry, without oil or accessories. The engine measured 55 inches in diameter and 74 inches in length. It incorporated technology and design features that pushed available metallurgy and manufacturing precision to their limits. The duplex Cyclone used 2 rows of 9 cylinders arranged radially around a central crankshaft. Each cylinder displaced 58 cubic inches. Total displacement exceeded 3,350 cubic inches. Hence the designation R3350. This displacement was among the largest of any production aircraft engine of its era. The enormous displacement allowed the engine to produce extraordinary power, but also created cooling challenges that would plague the design. Throughout its development, the engine used a 2-stage supercharger to maintain power output at high altitude where thin air normally caused power to drop dramatically. A supercharger is essentially an air compressor driven by the engine to increase the density of air entering the cylinders. More dense air allows more fuel to be burned, which produces more power. At sea level, a supercharged engine can produce more power than a naturally aspirated engine of the same displacement. At altitude, where atmospheric pressure drops and air becomes less dense, a supercharger becomes essential to maintain power. A single-stage supercharger provides boost at 1 compression ratio. This works adequately at moderate altitudes, but becomes inefficient at extreme altitudes, where enormous compression ratios are needed. A 2-stage supercharger uses 2 compressor stages in series, with the first stage compressing air to an intermediate pressure and the second stage compressing it further to the final pressure. This arrangement is more efficient at high altitudes and allows the engine to maintain useful power at heights where systems would be inadequate. The R3350's 2-stage supercharger used exhaust-driven turbines to power the compressor stages. Exhaust gases from the cylinders passed through turbine wheels, causing them to spin. These turbine wheels drove the compressor impellers through gearing. At maximum power settings, the turbine wheels operated at temperatures exceeding 1,000 degrees Celsius, hot enough to cause visible red glow in darkness. The turbine blades rotated at speeds approaching 20,000 revolutions per minute. At these rotational speeds, centrifugal forces on the turbine blades were enormous. The blades had to withstand not only extreme temperatures but also extreme mechanical stress. Minor imbalances in the turbine assembly could cause vibrations that would quickly destroy bearings or crack turbine blades. The materials used for turbine construction had to resist both high temperature and high stress simultaneously. The metallurgy available in 1940 was barely adequate for these requirements. Right engineers used exotic alloys and precise manufacturing techniques to produce turbine components that could survive the operating conditions, but reliability remained marginal throughout the engine's development. Cooling problems emerged as the most serious issue plaguing the R3350. Throughout its development and operational service, the engine produced approximately 2,200 horsepower from a compact package measuring 55 inches in diameter. This power density created heat that had to be dissipated through the cylinder cooling fins into the air flowing past the engine. The radial arrangement, with cylinders arranged around the crankshaft like spokes on a wheel, created inherent cooling challenges. The front cylinders received direct airflow as the aircraft moved through the air. These front cylinders cooled adequately under most conditions, but the rear cylinders were partially blocked from cooling airflow by the front cylinders. The air that reached the rear cylinders had already been heated by passing over the front cylinders. This meant that rear cylinders operated at higher temperatures than front cylinders, despite producing the same power. At high power settings, particularly during takeoff and climb, rear cylinders frequently overheated to temperatures where cylinder heads cracked or exhaust valves burned. Right engineers struggled with this cooling imbalance throughout 1941 and 1942. Modifications to improve cooling airflow often reduced power output or increased weight. Changes to baffle plates that directed air around cylinders sometimes improved rear cylinder cooling while causing front cylinders to run to cool, which created different problems. Adjustments to cylinder fin design increased cooling capacity but added weight and manufacturing complexity. The cooling system design for the entire engine installation became a critical focus of Boeing engineering efforts. The engine cowling, the metal shroud that enclosed the engine, had to direct cooling air efficiently over all cylinders while also maintaining aerodynamic smoothness. Early cowling designs created turbulent airflow that cooled poorly. Boeing engineers developed new cowling shapes with carefully designed inlet and outlet openings. They added adjustable cowl flaps at the rear of the cowling that could be opened to increase cooling airflow or closed to reduce drag. They designed baffle plates inside the cowling that forced air to flow over rear cylinders before escaping. They added oil coolers and intercoolers in the airflow path to dissipate heat from engine oil and supercharger compressed air. Each modification improved cooling incrementally, but rear cylinder overheating remained a persistent problem throughout the B-29's operational career. Pilots learned to manage engine temperatures carefully, reducing power settings during climb to keep cylinder head temperatures within limits even if this extended the time required to reach altitude. Maintenance crews learned to expect frequent cylinder changes as rear cylinders failed from overheating. The cooling problems were never completely solved, but they were managed adequately to permit operations. The first B-29 prototype flew on September 21, 1942. Test pilot Edmund Allen commanded the flight from Boeing Field in Seattle. Allen was one of America's most experienced test pilots, having flown first flights of numerous Boeing designs, including variants of the B-17. He was assisted by co-pilot Robert Lamson, flight engineer Charles Benton, and several engineering observers. The flight lasted 75 minutes and covered basic handling characteristics, engine performance, and pressurization system functionality. The aircraft took off from Boeing Field at approximately 12:30 hours. Allen conducted a gentle climb to 10,000 feet, evaluating control, response, and engine behavior during climb. The pressurization system was activated during climb, with cabin pressure maintained at the equivalent of 8,000 feet, while the aircraft climbed to increasingly higher altitudes. This test confirmed that the system could maintain pressure differential as designed. Allen noted in his verbal report immediately after landing that the cabin environment was remarkably comfortable compared to any other bomber he had flown. The temperature remained moderate, despite the aircraft operating at altitude where outside air temperature was well below freezing. The noise level inside the pressurized cabin was significantly lower than in an aircraft because the pressure vessel structure also provided sound insulation, but the flight also revealed problems that would require extensive modification. Cylinder head temperatures ran higher than acceptable limits during climb. Allen reported that several rear cylinders on both outboard engines approached redline temperatures. Oil consumption measurements after the flight showed that engines used oil at rates exceeding predictions, suggesting that piston rings or valve guides were wearing rapidly. Vibration levels in the engine mounts were higher than comfortable, though not dangerous. The vibration transmitted through the airframe structure created noise and discomfort for crew members. Allen's written report, filed the following day, noted that the aircraft met performance requirements for speed and altitude. The pressurization system worked as designed. Control response was adequate though heavy at high speeds, but the report emphasized that engine reliability must improve dramatically before operational service could begin. The cylinder head temperature problems required immediate attention. The oil consumption rates were unacceptable for operational missions. The vibration issues needed resolution to prevent fatigue. Damage to airframe structure over time. On February 18, 1943, the second B-29 prototype suffered the catastrophic failure that nearly destroyed the entire program and forced fundamental redesigns of engine installations. Edmund Allen was again at the controls, conducting engine testing at altitude with a crew of 10 Boeing employees and Wright engineering representatives. The flight plan called for testing engine performance under various power settings and conditions. At approximately 12:15 hours, the aircraft departed Boeing Field and climbed to 5,000 feet. Allen conducted a series of tests over the next 90 minutes, documenting engine temperatures, fuel consumption, and performance characteristics. At approximately 13:45 hours, while the aircraft was approximately 20 miles southeast of Boeing Field, fire erupted in the wing area between the number 1 and number 2 engines on the left side. The exact cause was never definitively determined because the aircraft was destroyed in the subsequent crash, but investigators believe that either a supercharger failure or a cracked cylinder allowed burning oil or fuel to escape from the engine. The fire ignited aluminum structure and hydraulic fluid, creating an intense fire fed by multiple fuel sources. Allen immediately shut down both left engines and initiated emergency procedures for engine fire. He activated the engine fire suppression systems, which flooded the engine nacelles with carbon dioxide to smother the flames. He initiated emergency descent toward Boeing Field, approximately 20 miles distant. The co-pilot transmitted a distress call, indicating that the aircraft was on fire and attempting emergency landing. Ground observers at Boeing Field and in surrounding areas reported seeing the B-29 with flames streaming from the left wing. The fire intensified despite Allen's actions. The flames burned through wing structure, weakening critical spars that carried flight loads. At approximately 13:50 hours, when the aircraft was approximately 5 miles from Boeing Field and descending through 2,000 feet, the wing structure failed catastrophically. The outer section of the left wing separated from the aircraft. The sudden loss of lift on the left side caused the aircraft to roll inverted. Allen attempted to recover, but the aircraft was uncontrollable with major wing structure missing. The B-29 plunged nearly vertically into the Fry & Company meatpacking plant in Seattle's Georgetown district. The impact and subsequent fire killed all 11 men aboard the aircraft. Allen, co-pilot Lamson, flight engineer Benton, and 8 observers died instantly in the crash. The aircraft struck the packing plant with sufficient force to penetrate the roof and ignite a fire that consumed much of the building. 20 workers in the packing plant also died, trapped by the fire or killed by falling debris. Another 20 workers were seriously injured. The crash created a crater in the concrete floor of the packing plant. Wreckage was scattered across an area measuring approximately 100 feet in diameter. The intense post-crash fire destroyed most evidence that might have revealed the exact cause of the in-flight fire. Investigators from Boeing, Wright, and the Army Air Forces conducted extensive examination of the wreckage and interviewed witnesses who had observed the aircraft in flight. The consensus was that the fire originated in the number 1 engine, likely from either supercharger failure or cracked cylinder, and that the existing fireproof bulkheads between engine and wing structure were inadequate to contain the fire long enough for Allen to reach an airport. The crash threatened to end the B-29 program entirely and forced fundamental reconsideration of whether the aircraft could be made safe enough for operational service. Critics in the Army Air Forces and in Congress argued that the aircraft was too complex, too ambitious, too experimental for wartime production. The engine problems alone suggested that the design was fundamentally flawed. Wright had struggled with R3350 reliability since the engine's first tests. The crash of the second prototype, following months of mediocre test results, indicated that the problems might be insurmountable. Development costs had already exceeded $3 billion, more than any military program in American history, except the Manhattan Project, which was developing atomic weapons. Production commitments called for building thousands of B-29s at factories in Washington, Kansas, Georgia, and Nebraska. Contracts had been signed, factories had been built, tools had been designed, workers had been trained. Canceling the program would waste those investments and leave the Army without a strategic bomber capable of striking Japan from distant bases. But continuing the program risked more crashes, more deaths, and potential failure of a critical weapons system that had consumed resources that might have been used for proven designs like additional B-17s or B-24s. The decision to continue came from the highest levels of American military command. General Henry Arnold, commanding general of the Army Air Forces, committed his personal authority and reputation to the B-29 program. Arnold understood that the strategic bombing campaign against Japan would require capabilities beyond those of existing bombers. The B-17 and B-24, excellent aircraft for operations from British bases against European targets, lacked the range to strike Japan from bases that American forces could realistically establish and defend. The B-29, despite its problems, offered the only pathway to strategic bombing of the Japanese homeland. Arnold ordered development to continue, production to accelerate, and combat operations to begin regardless of remaining problems. He personally assumed responsibility for the program's success or failure. He directed that resources be devoted to solving the engine fire problems immediately. He established aggressive timelines for modifications and testing. He accepted the risks inherent in fielding an aircraft before all problems were resolved, calculating that the strategic necessity outweighed the tactical risks. The solution to engine fire problems required redesigning the entire engine, installation and fireproofing systems throughout the wing structure. Boeing engineers repositioned engines slightly further from the fuselage, increasing clearance between nacelles and wing structure from approximately 18 inches to 24 inches. This additional separation provided space for improved fireproof bulkheads and gave fires more distance to travel before reaching critical wing structure. They installed fireproof bulkheads constructed from stainless steel rather than aluminum between engines and fuel tanks. These bulkheads were designed to contain engine fires for at least 15 minutes, providing time for crew to shut down engines, activate fire suppression systems, and potentially reach an emergency landing field. They added fire detection systems throughout the nacelles and wing areas. These systems used thermocouples to detect temperature increases that indicated fire before flames became visible. The detection systems provided early warning that allowed crew to respond before fires became uncontrollable. They developed improved fire suppression systems that could flood engine compartments with carbon dioxide to smother fires. The systems included larger carbon dioxide bottles and distribution piping that ensured rapid discharge throughout the engine nacelle. They modified cowling panels to improve cooling airflow while maintaining aerodynamic efficiency. The new cowling designs incorporated larger inlet areas and adjustable outlet flaps that provided better control over cooling airflow. They strengthened engine mounts to reduce vibration that could cause fuel lines to crack or electrical connections to fail. The new mounts used rubber isolation bushings that absorbed engine vibration before it transmitted to the airframe. They added fire-resistant materials throughout the wing area. Hydraulic lines were rerouted to run outside areas where engine fires were most likely. Electrical wiring was protected with fire-resistant insulation. Fuel lines incorporated fire sleeves that would contain leaking fuel, even if the line was damaged by heat or fragments. Every change added weight. Every modification required testing to ensure it did not create new problems. Every improvement demanded engineering hours that delayed production and consumed resources. The modifications added approximately 400 pounds to each aircraft's empty weight, but the modifications worked, reducing engine fire risk to acceptable levels. By late 1943, B-29s were flying with significantly reduced fire risk, though engine problems persisted. Engines still overheated during extended hyperoperations, requiring pilots to manage power settings carefully. Maintenance requirements remained intensive, with engines often requiring cylinder changes after relatively few flight hours. Reliability was lower than desired, with engine failures occurring frequently enough to create operational challenges, but the aircraft could complete missions and return crews home safely with acceptable regularity. The fire protection improvements meant that engine problems, while still serious, were no longer immediately catastrophic. Crews had time to shut down failing engines and execute emergency procedures. The modifications represented a compromise between ideal reliability and operational necessity. The B-29 would never have the engine reliability of the B-17 or B-24, but it provided capabilities that those aircraft could not match. And the engine problems, while frustrating, were manageable within operational context. The defensive armament system represented another revolutionary feature that added significant complexity and weight, but dramatically improved crew effectiveness. The B-29 carried 10 12.7mm Browning M2 machine guns and one 20mm on M2 cannon arranged in 5 turrets. 4 turrets, to dorsal and to ventral, were remotely controlled through a sophisticated analog computer fire control system developed by General Electric. The tail turret, mounting the 20mm cannon and 2 machine guns, was manually controlled by the tail gunner. This mixed arrangement reflected the different tactical requirements for forward and rear defense. Attacks from the forward hemisphere, where most Japanese fighter interceptions occurred, required rapid response and accurate fire under difficult conditions. Remote control allowed gunners to operate from stable sighting positions inside the pressurized cabin rather than standing at gun positions exposed to airflow and vibration. Attacks from the rear hemisphere were less common but required heavy firepower. The tail turret's manual control provided the tail gunner with direct control over the aircraft's most powerful defensive position. The remote gun system fundamentally changed how aerial gunners operated. Traditional, manually operated gun positions required gunners to stand at their guns, exposed to wind, cold, and noise. The gunner physically aimed the guns by moving them with mechanical controls or direct hand pressure. This arrangement placed gunners in difficult working conditions that degraded their effectiveness. At high altitude, temperatures dropped to -40 degrees Celsius. Wind noise made communication difficult. Oxygen masks restricted breathing and vision. The physical demands of standing at gun positions for hours while wearing bulky heated suits, oxygen equipment, and parachutes exhausted gunners before combat even began. The remote system transformed this environment. Gunners sat at sighting stations inside the pressurized cabin, comfortable in shirt-sleeve conditions. They observed the sky through optically flat glass panels that provided clear vision without distortion. They wore no oxygen masks, no heated suits, no bulky equipment. They could communicate icily through the intercom system. They remained fresh and alert throughout missions lasting 10 to 12 hours. The gunner tracked targets using control handles connected to the fire control computer. The handles resembled small steering wheels. Moving the handles left or right caused the remote turret to traverse in the corresponding direction. Moving them up or down caused the guns to elevate or depress. The gunner simply kept the target centered in his optical sight. The computer did everything else. The General Electric Fire Control System calculated lead angles based on target motion, adjusted for aircraft speed and altitude, compensated for gravity drop and air resistance affecting bullet trajectory, and automatically aimed the guns to hit the target. The system incorporated gyroscopes that measured aircraft attitude and turn rates. Gyroscopes are spinning masses that resist changes in orientation. When mounted in gimbals, they provide reference information about aircraft motion independent of visual cues. The fire control system used this gyroscopic information to stabilize gun pointing even when the bomber maneuvered. Airspeed sensors provided velocity information that the computer used to calculate bullet time of flight. Altitude sensors indicated barometric pressure, which affected air density and therefore bullet trajectory. Temperature sensors measured outside air temperature, which also affected ballistics. The computer combined these inputs with gunner tracking information to calculate where guns should aim to hit a moving target from a moving platform at high altitude. The computation had to occur continuously in real time as both bomber and fighter maneuvered. The system represented the most sophisticated analog computer ever installed in an aircraft as of 1943. It used mechanical computing elements, including gears, cams, differentials, and resolvers to perform trigonometric calculations continuously. Electrical motors drove the computing mechanisms and powered the gun turrets. The entire system consumed approximately 3,000 watts of electrical power, requiring generators on each engine to supply adequate electricity. The system worked remarkably well when properly maintained and calibrated. Gunners reported that the computerized aim was more accurate than manual aiming, particularly at long range where lead angles were large and difficult to estimate visually. But the system required extensive training for gunners to operate effectively. Maintenance procedures were complex and time-consuming, requiring specialized technicians who understood both mechanical and electrical systems. Component failures could disable entire turrets, reducing defensive capability until repairs could be completed. The weight penalty for the remote control system exceeded 2,000 pounds compared to conventional manually operated gun positions. This weight included the sighting stations, fire control computer, electrical motors, mechanical linkages, turret mechanisms, ammunition feed systems, and electrical power systems. Each turret weighed approximately 400 pounds more than an equivalent manually operated position. The 4 remote turrets added 1,600 pounds. The fire control computer and associated equipment added another 400 pounds. This substantial weight penalty consumed payload capacity that might otherwise carry additional bombs or fuel, but the system proved its worth in combat by allowing gunners to operate effectively in conditions where manual gun operation would have been nearly impossible. The pressurized environment permitted sustained operations at altitudes where unpressurized manual positions would have exhausted crews within an hour or two. The first B-29 combat mission occurred on June 5, 1944, when 98 bombers from the 20th Bomber Command departed bases in India to strike railroad targets in Bangkok, Thailand. The mission represented the culmination of 3 years of development and reflected both the capabilities and continuing limitations of the aircraft. The bombers departed from bases around Karagar, India, where B-29 units had deployed after completing training in the United States. The flight to Bangkok covered approximately 1,200 miles, requiring 5 hours of flying time. The bombers flew at altitudes between 20,000 and 27,000 feet, high enough to be beyond reach of most anti-aircraft guns, but low enough to ensure bomb accuracy. Weather was generally favorable with broken clouds that did not obscure targets. Japanese fighter opposition was minimal, since few fighters were stationed in Thailand, and most of those present lacked the performance to intercept effectively at B-29 operating altitudes. The mission demonstrated both the B capabilities and continuing operational problems. 14 aircraft aborted before reaching targets due to engine failures or mechanical problems. This represented approximately 14% of the attacking force. An unacceptably high rate that indicated reliability remained problematic. The aborts occurred throughout the mission profile, 2 aircraft turned back shortly after takeoff when engines failed during climb. Several more aborted while en route to targets when engine problems developed. 3 aircraft turned back from the target area when bomb bay doors failed to open properly. The common thread in most aborts was engine-related problems. Cylinder head temperatures exceeded limits, forcing pilots to shut down engines before catastrophic failure occurred. Oil pressure dropped to dangerous levels, indicating possible bearing failures. Vibration levels increased suddenly, suggesting internal engine damage. Each abort represented a mission failure for that crew, and reduced the total weight of bombs delivered to targets. 5 aircraft were lost to various causes, though none to enemy action. 2 aircraft crashed in India when landing gear failed on return.